What we're really going to talk about in this lesson is the acceleration due to gravity. When we drop things, things fall down, and at a known reproducible rate that is always changing, right? In other words, we drop something and it speeds up over time. So that's called an acceleration, right? So what we want to do is introduce the gravitational acceleration. We'll talk about what it is, what the value of it is, and then we're going to talk about one of the most, like I mean it when I say it, one of the most interesting, fundamental, mind-blowing things in all of physics. And that is when you take two objects and you drop them, even if the masses are different, they will hit the ground at the same time. I encourage you to try it. Grab a marker, something like this, grab a paper clip, drop them at the same time from the same height, and they will hit the ground at the same time. The only time in which it doesn't really happen is if I drop the sheet of paper, it's going to flutter to the ground, but that's only because of air resistance. So if you suck all the air out of a container, like in a vacuum chamber, or if you go to the moon, for instance, where there is very little or no oxygen on the moon, no atmosphere, then literally any two objects you drop will hit the ground at the same time. In fact, we did this experiment on the moon where astronauts dropped a feather in one hand and a hammer with the other. In the other hand, there's no air to slow anything down. On Earth, the feather will flutter down, but on the moon, they just both went down toward the ground and hit the surface of the moon at the same time. So we want to talk about that. If you stick around to the end of this lesson, you will understand about all that we know about why this actually happens. And it is still one of the most interesting, not totally well understood ideas in all of physics, but we can certainly get to the meat of the matter and talk about it. So before we get to that, we want to talk about gravitational acceleration. So gravitational acceleration. Now, in the last few lessons, we've been talking about things accelerating, and that was always on the x-axis here in one direction. Now, when we talk about things moving in the up and down direction on Earth, on Earth here, we call it the y direction. And because we're dealing in the y direction, the acceleration that you feel in the up and down direction is the acceleration due to the gravitational force of attraction between the Earth and all the bodies that surround the Earth, okay? So what we say then is that the gravitational acceleration g is equal to the value of 9.8 meters per second squared. It's really 9.81 with a bunch of decimals after it, but this is a good approximation to solve pretty much all physics problems, 9.8 meters per second squared. So what this unit means is 9.8 and meters per second squared. Don't forget what it means. It means meters per second in the top per second. That's meters per second squared. So this is how much your velocity increases every second. So if I drop something, after the first second, it is going from rest. Now at the first second, it's traveling at 9.8 meters per second. But after the next second, it picks up an extra 9.8 meters per second velocity. After the next second, it picks up another one and another one. So every second, it's picking up 9.8 meters per second. That's why it's called 9.8 meters per second, which is 9.8 meters per second squared. All right, now, in all of our equations of motion, these are, remember, our equations of motion. We're going to use these to solve problems in a minute. But our equations of motion, we have the acceleration a. So what we're going to actually do is we're going to use the exact same equations of motion, but we're going to say that the acceleration a is equal to negative g, which is negative 9.8 meters per second squared. Now you might say, why is he putting a negative sign in here? Well, it's because when we are dealing in the horizontal direction, we have the positive x direction and the negative x direction. And when we're dealing in the vertical direction, what we do is we say that we have a plus y direction up here and a negative y direction down here. So here's the 0 point, which could be any reference point you want. It could be the ground, for instance. And then going up, we call it positive y. Going down, we call it negative y. But since gravity always acts downward, we call the letter g being equal to 9.8 meters per second squared. The acceleration, when we put the correct sign on it, we say it's negative 9.8 meters per second squared because the acceleration of gravity acts down towards the ground. So when we solve all of the problems involving motion due to gravity, then since we choose the up direction to be positive y, the acceleration is always acting opposite to the up direction, so it's negative g, or negative 9.8 meters per second squared. So what we're going to do in a minute to solve these problems is we're going to transform these equations very, very simply into equations we can use in the up and down direction. We call this free fall acceleration problems. But before we get to that, I want to tackle one of the most interesting things in all of physics. And that is, let's go back to the idea that if we stand here and if you drop a bowling ball, which is very heavy, and a paper clip or a pencil, then actually they will hit the ground at the same time. In fact, if you take a car, a vehicle, a dump truck, a gigantic, wrecking ball, anything, and you suspend it in the air, it's very massive, very heavy. And you also grab a pencil, and if you could ignore air resistance and you let them drop at the same time, the very heavy object accelerates down and hits the ground at exactly the same time as the lighter object. If you ever see that not happening on Earth, it's only because the air is in the way. You take the air out of the equation, as on the moon, they always hit the ground at the same time, no matter what the difference in the mass is between the objects. Now you might say, how is that possible? People have been pondering this for years, thousands of years, right? Because it seems like a heavier object should hit the ground first. Why? Because we know that heavy objects are pulled towards the ground more. So if they're pulled to the ground more, they should accelerate more and they should hit the ground more at a sooner or a smaller amount of time. So why is it when we do this experiment, and I encourage you, do it. Go grab a marker, go grab a penny or something small and drop them. And you'll see that they always hit the ground at the same time. Why is it? We know the more massive object is attracted more and has a higher force of gravity. So why doesn't it just accelerate more and hit the ground at the same time? Well, in order to do that, we need to talk a little bit about some things we haven't discussed in physics yet. So I'm going to get a little bit ahead of where we are. We're going to talk about gravitational force, and we're going to talk about one of Newton's laws of motion. We haven't really had those lessons yet, but I don't want to wait because it really is one of the most interesting things in all of physics, and I just can't teach this lesson on gravitational acceleration without sharing with you one of the most amazing things you could ever learn. Why is it that two different objects of two different masses hit the ground at the same time? So we're going to get a little ahead of ourselves, but then we will catch up and we will hit gravity and some other topics a little more thoroughly later on. So the first thing we need to understand in order to understand this is we have the force of gravity. Right? So the force of gravity is a famous equation. Here's what it is. The force of gravity, you call it F sub g if you want, right? You have a little object here. It's got some mass. There's some earth down here. Let's call this earth, right? And there is some force acting on this mass. Because the earth has some mass, big M, I'm going to call it big M, and we're going to call it big M with a little E on the bottom because this is the earth mass, gigantic thing, right? And then we have a smaller mass, which is you or me or anything else, and it's sitting up there and has a mass little m, okay? Now we know from experience that there is a force acting on this thing. We're going to call it F sub g because it's a force of gravity. If the thing is over here or over here or over here, the force of gravity always acts toward the center of the planet. So the people on the other side of the planet are pulled kind of up to their local ground, and everybody is being attracted toward the center with F sub g, the force of gravity. And we already know that the more massive you are, the more force of gravity you feel. A car has more force of gravity than this marker, for instance. So this force of gravity is called F sub g, and it's a famous equation, right? And here's what it is. It's the gravitational constant of the universe, g. We could look up that number later on. And then it's multiplied by little m, and then multiplied by big M, and then divided by r squared. So, it's an equation, but as equations go, it's not that complicated. Basically, you have a constant of the universe called g. This is the gravitational constant that governs everything. We could look the number up in a book, but honestly, the number doesn't matter. It's a constant we can look up. Big M, little m, divided by r squared. So you can see right away that if you make the mass of yourself bigger, then force of gravity gets bigger. If you make the mass of the Earth bigger, that's going to be mass of the Earth right here, then the force of gravity gets bigger. If you change the constant of the universe and make it bigger, then the force of gravity gets bigger, but that constant doesn't change as far as we know. Now, what if the distance between the object, because this is the distance, r, between the center, I've drawn it to the surface, but really it's to the center of the Earth here. So I guess I could clarify that. Just say this r is to the center of mass of the Earth there. If we make the distance bigger between the two objects, then this number gets bigger and the force of gravity goes down. And that makes sense because if I pull something far away from the Earth, we expect there to be less gravity. And that's what happens. If we go, thousands of kilometers away, the force of gravity is smaller because the distance is is bigger, and so we divide by a big number, we get a small gravity. If we get close to the surface and make this very small number, then this number gets bigger. So this is the force of gravity, right? Now the next thing we need to know is something called Newton's law. One of Newton's law of motion. We're going to talk about this a lot more later, right? What we have with Newton's law is a famous equation called F is equal to ma. This is the force acting on an object is equal to the mass of the object. Notice it's little m, same little m as over here, times its acceleration. This is, there's a joke that says that if you know F equals ma, the Newton's law of motion, then you can solve almost any physics problem, because most physics problems, a lot of them, boil down to just knowing how to use that equation properly. And we're going to use that equation a lot coming up. But what I want you to know and pick up from this equation is this is kind of like the law of inertia. You know, you already know that if you were to go into deep space and you push on something, like a spacecraft or a basketball, then it should start moving, right? So this equation tells me if I push on something, that's what a force is, the acceleration that happens is related by this equation. If I know the mass of the object and I push on the object, then I can calculate the acceleration that the object will have, because it's going to start to move. Now, you know from just dealing with things on the ground, if I go behind a giant semi-truck, which has a lot of mass, and I push on it, it's very hard to move. But if I go up to a tennis ball with a low mass, it's very easy to move. That's what we call inertia. It has nothing to do with gravity. Go into deep space with a semi-truck and try to push it. It's going to move, but it's going to be really hard to get moving, even though there's no gravity, okay? Tennis ball in space, very easy to move. It's because the mass is different. Somehow, the mass of an object resists motion, right? When you have more mass in an object, it resists your push. It does start moving, but it takes, more effort to move it, right? And to accelerate it. Whereas something that has very little mass seems to move very easily when we push on it, right? This equation is what governs that, right? Because what I'm saying is that, let's say I have a small mass here, and then I apply some force to it. Then what's going to happen is I'm going to get some acceleration out of it. But what happens if I make this thing big, like gigantic, like as big as a spacecraft or a semi-truck? Very, very, very large force, right? Very large mass, okay? Then in order to get it moving with the same acceleration, then I have to apply a big force, because let's say that I want two things to move. This is another way to look at it. Let's say I want two things to move at the same acceleration, right? If I make the mass bigger and the acceleration is the same, I have to apply more force to make it happen. If the acceleration is the same and I make the mass smaller, like if I dial this down really, really, really little, then it doesn't require as much force, because these are multiplied together. If I want two different things to accelerate at the same rate and they have different masses, if you increase the mass, the force must be higher, because this product is going to be bigger, and the force required to move something is equal to its mass times its acceleration. All right? Now, there's two different things that we've just talked about. This is talking about how hard it is to move something, how much force is required to get something to move. And this is involving the force of gravity acting on two things. Now, let's say that we have this object here, and we suddenly let it go and allow it to move. Then what we're saying is we have a force of gravity, which is this, but this is the same force that's acting on this side of the equation. So how will it move? That's the fundamental thing, right? Because this force is the force of gravity, and we're saying that any force you apply causes things to accelerate, according to this equation, then if we set these forces equal, we can calculate the acceleration of anything because of the force of gravity, or due to the force of gravity. So what you have here on the left is you say g times little m times big M. This is the mass of the Earth times the mass of the object divided by r squared. And this is equal to the force of gravity, which is also equal to the force I'm applying to the object, which is equal to m mass times acceleration. So all we've done is take the force of gravity and make it the force that's acting on any body, which is mass times acceleration. Now I want you to notice something extremely profound, and the first time you see it, it doesn't seem profound. It just seems, oh, it's an equation, whatever. But it's very profound. What we see is that on the left-hand side of the equation, we have a mass here, little m, which is the mass of the object, and we have another little m on the right-hand side. So what that means is I can divide both sides of this equation by little m, because this is an equation. I can do whatever I want to both sides. So I choose to divide this by m and divide this by m, which means these m's cancel. What it means is that the mass on the left and the mass on the right are in balance, and they kind of annihilate each other, and they don't matter in the final analysis. Even though the force of gravity depends on mass, and the force and the acceleration equation for Newton's law also depends on mass, because they're on both sides of the equal sign, they both balance each other out, and so the net result of the acceleration due to gravity doesn't depend on mass, because you can then see, once I flip this thing around, that the acceleration due to gravity is equal just to this gravitational constant of the universe multiplied by the mass of the Earth divided by r squared. Okay? This is the acceleration that anything feels inside of a gravitational field. It depends on the gravitational constant of the universe, it depends on the mass of the planet, and it depends on how far apart those two things are. But it doesn't depend on the mass of the object you drop. That's why when we drop a feather on the moon, and we drop a pencil here and a paper clip, they have very different masses. The pencil is pulled down with a higher force of gravity, but they both hit the ground at the same time. They both accelerate at the same rate, because when we set the force of gravity equal into Newton's law, the mass on both sides completely cancels, and so the acceleration of gravity does not depend on the mass of the object. That means all objects must fall at the same rate. I'll say it again. That means all objects must fall at the same rate. So if I go to the moon, of course, this becomes mass of the moon, and the acceleration of gravity is less. If I go to Mars, the mass of Mars goes in here, then it's less. If I go to the sun is way more massive than the Earth, the acceleration of gravity is much higher. But on any of those bodies, if you take two objects and drop them, they will accelerate at the same rate. Now, I could stop there, because that's pretty much the punchline. Most students want to know, why do they fall at the same rate? Here we go. Force of gravity, force equals mass times acceleration, and then we set them equal. So we could just stop there and say, okay, we get it now, we understand. But let's just take it let's squeeze as much understanding as we can out of this. Let's just think through a little logical situation. Let's say that I have a situation with an object, and I know it has a force of gravity, and that force of gravity then gets turned into, for lack of a better word, an acceleration according to this equation. Let's say, what would happen if I then increase the mass of the object, make it heavier, make it 1,000 times heavier? Then, because of this equation, because it's multiplied in the top, then because you made it more massive, it has 1,000 times the force of gravity acting on it. So that's why when we think about this as a everyday understanding, we think, well, heavier things should fall faster, because we know it's being pulled down more. This side of the situation, we all understand intuitively. Make it 1,000 times more massive, then we have 1,000 times more force, okay? But then if you take that 1,000 times more force and put it into this side, and calculate the acceleration, how fast or the rate of change of its velocity is it going to go down, then you might think, well, it's 1,000 times more force, so I should expect 1,000 times more acceleration. But the problem is, the only way you were able to get the 1,000 times extra force is because you made the mass 1,000 times more massive. So you did have the 1,000 times force here, but the way you did it is you have to make the same mass over here 1,000 times more. So yes, you made it 1,000 times more attractive to the ground, but because you made it 1,000 times more massive, they cancel. And so when you divide this out, the acceleration becomes exactly the same as it was in the other case. Because yes, the thing is pulled to the ground with more force, but to get something that's more massive to move requires more force. And those two things cancel out, so the acceleration is always the same. I'm going to say that one more time because, it's something that we need to digest. Sometimes you don't want to blow through major conclusions. What we're saying is that when we make something more massive, we do get more force. And so we do have more force acting in Newton's laws. But when more force of gravity, so we think it's going to move faster. But the problem is, to get something that's more massive to move in the first place requires more force, because if you go into deep space and you push on a bulldozer, it's going to resist your motion. It has more inertia. So this is called the inertial mass of the object. Inertial mass, that's actually a word. Inertial mass. And this thing over here is called the gravitational mass. And it turns out that the gravitational mass and the inertial mass are the same, they're the same value, right? The gravitational mass determines how much force it's going to act on the object, the inertial mass determines how much it kind of resists your motion. And because the inertial mass and the gravitational mass are the same, have the same value, and they're on both sides of the equation, yes, you get a lot more force with a really massive object, but that really massive object requires a ton more force to actually get to move. And so because of that, they balance each other out exactly, because the mass is on both sides and the acceleration of gravity acting on anything, therefore, is always the same thing. Always the same value. So we have talked about the gravitational acceleration. We said that it's equal to 9.8 meters per second squared. We called it g. And then we talked about why things fall at the same rate and why two different objects of two different masses fall at the same rate. Because of, that's the way gravity works, then when we do these motion problems, where we drop things, we don't usually care too much about the mass of the object. If you notice, in the problems, it won't tell you that the baseball was 5 milligrams or whatever it is, or half a kilogram or anything. It usually won't even specify the mass, and that's because we know that the objects that move in a gravitational field, when we throw them, like an arc or anything like this, the path of the arc does not depend on the mass, and that's because when things fall, they all fall at the same rate. The acceleration of gravity is the same for all objects. So what we can do is we can look at the equations of motion that we have written down before, and we can change them very slightly to be applied or applicable to vertical motion in a gravitational field with gravitational acceleration. So I can change this to say equations of motion. It is constant acceleration, yes, and we can call it free fall. So in some books you see this as free fall acceleration problem. Some books you'll see it as gravitational acceleration motion equations. There's lots of different words for it, but basically these equations of motion, they all have acceleration in them. And the way we talked about it before is the acceleration has to be constant. It has to never change. Okay, so what we can do is assume that the gravitational acceleration doesn't change, and we can change these equations of motion, right? Because we now see v is equal to v naught plus at. Instead of talking about this happening in the x direction, what we'll do is we'll turn it on its side and talk about motion in the y direction. But what we will do is, instead of the acceleration a being here, we'll change the equation and we'll change it to minus g. You see, all we did was change the acceleration of gravity to be turned into negative g, where g is 9.8. So what you're really doing is you're substituting negative 9.8 in for the acceleration a. So you have a negative sign, and then a 9.8 here, which is a number, and then times time. So this equation is now transformed, and we can use it for free fall problems. The missing quantity in this equation, we're not talking about x's anymore, we're talking about y. So y minus y naught. There's no distance anywhere in this equation. Right? Then we can go to the next equation and say, okay, we have x's here. We'll change the x's into y's because we're talking about the y direction. So we'll have y minus y naught, v naught in the y direction, t plus 1/2 at squared. So we'll change the a into negative g, so then the negative sign comes out. And so this equation turns into y minus y naught is v naught t minus 1/2 gt squared. The missing quantity is the final velocity v. Then we will take this equation of motion, which we've been using forever, and we will change the a here, the acceleration that's happening in this problem, equal to negative g. So we'll just turn this guy into here. And then we have the x and the x naught. We'll change this into y minus y naught. The missing quantity is time. And then in the next equation, we will take this x minus x naught and we'll change it to y minus y naught, because these are the distances in the y direction. V naught t, v naught plus v parentheses t, so that's all the same. The missing quantity, we did have it listed as a, the acceleration before. We're just going to put it as g. Here, that's the missing quantity. And then the last one that we're going to change is the x's turn into y, so we have y minus y naught, vt minus 1. Now this is, a has to be turned into negative g, so this turns into negative g, but that negative gets multiplied by this and turns it into a positive. So when you look in your book, these are the equations of motion that we're going to use in the free fall acceleration, which is purely vertical acceleration happening towards the Earth's surface due to the acceleration due to gravity. And so what we have, just checking myself, v is v naught minus gt. with a missing quantity y minus y naught. Then y minus y naught, it was v naught t minus 1/2 gt squared with a missing quantity of v. V squared equals v naught squared minus 2g y minus y naught missing quantity of t. Y minus y naught is 1/2 v naught plus v times t missing quantity of g. And then y minus y naught vt plus 1/2 gt squared missing quantity v naught. The reason I'm doing it this way, instead of just writing the equations again, is because students think when they solve the first set, use the first set of equations for motion in the x direction, that there's like a totally separate set of equations for the vertical motion, but I'm just showing you that it's literally the same set of equations. In fact, some books don't even put these equations down. They just leave everything in terms of the acceleration a, and then when you put the problem in place, you just substitute a as being negative g, because that's always the free fall acceleration due to gravity. It's always the same value. And you can see that we just erase and change and we get the new equations, but they're not really new. They just come from what we already know. All right? So these are the values that we're going to use. And the one thing I want to caution you about is that notice that all of these equations have a constant acceleration g. And I've told you many times that you can only use this when the acceleration that you have in your problem, it doesn't change. It's a constant acceleration. So in the previous problems, we always set it up to have a constant acceleration. Here I'm telling you to assume that g is constant, 9.8 meters per second squared. However, when we look over here, when we set the force of gravity, which is equal to this, and we set it equal to Newton's law, which we're going to get to later, equal to this, and we cancel the masses because mass doesn't affect the acceleration here, we found out the acceleration of gravity is basically equal to some constant of the universe times the mass of the Earth divided by r squared. So what we've learned is the acceleration of the gravity does depend on the distance you are from the center of the Earth. See, it's right here. It does depend on that. So this means that if an object actually starts here and then gets a little bit closer to the center of the Earth, technically g, which is 9.8 meters per second squared, it does change. It is slightly different from here to here, because we can see right here that the acceleration due to gravity, which we just kind of derived, it depends on the distance from the center of the planet. But what you find out in practice is that the difference in acceleration due to gravity on any of our problems that we solve is minuscule. You would have to go very far into space. I'm not sure. I don't want to give you a number because I'll probably get the number wrong. But you would have to go a fairly far distance away from the Earth so that the acceleration of gravity was different enough from 9.8 meters per second squared to affect the calculations very much. So even though we know that the acceleration of gravity is really not a constant, we know this, what we do is we simplify it for physics, a Physics 1 course, calculus-based, and we say, hey, we know that it's not actually constant, but what we're going to do is we know it's pretty darn constant on any problem we're going to solve in motion near the surface of the Earth, so we just say it's constant. But in the back of your mind, I want you to remember that it's really not constant, because if you're designing a rocket, or you're designing a spacecraft, or you're designing a space station, or anything that goes farther away from the planet's surface, then you cannot use these equations. They're going to give you wrong answers. The farther away you get, the more of a wrong answer you're going to have. And so we have to use calculus and other more advanced concepts we'll learn later about to handle the more complicated situations. All right, the very last thing I want to talk about is to discuss how this acceleration due to gravity affects an object. So we can have a falling object, right? So we can keep track of the time in seconds that an object falls. We can keep track of its position in meters. We can keep track of its velocity in meters per second, and we can keep track of its acceleration in meters per second squared. And what I want to do is I want to keep track of a hypothetical object here, right? And I want to say that this is the 0 point, let's say, and there is some object here. So I'm going to put the object in bright red, and it starts here. And when I say it's the 0 point, I mean this is the y-axis. So all the numbers down here are the negative y-axis. Going down, up here is the positive y-axis. So you could think of this as positive y going up here. Here's the 0 point. So how do we want to fill in this table? What happens at 0 seconds is the moment the experiment starts, the moment you let go of this marble, before anything happens. It has a position of 0 meters, because it hasn't moved down at all. It has a velocity of 0 meters per second, and its acceleration is what? Negative 9.8 meters per second squared. The acceleration of gravity is what is always acting on any object, no matter its motion. And we know it's not exactly constant, but we're assuming it's constant in a physics course because it doesn't change very much close to the Earth's surface. So then we come down here, and say, all right, let's take a look at 1 second in the future. So what we do is say, actually, I don't want to put the 1 there. Sorry about that. I want to take a look at looking 1 second in the future. So I'm in the 1 second column. The object has obviously moved down a bit from its original location. What we do is we say when we drop the object that this is the 0 point. So any distance we go down below the 0 point is a negative value of y. We have to have a reference. We just say 0 when we let it go, and when it drops down, we have a negative value of y. Well, let's take a look. What is the acceleration of this object? It's still negative 9.8 meters per second squared. So after 1 second happens, what is its velocity? See, acceleration is meters per second. And what it means is you're subtracting and you're going more and more negative by this amount. So after 1 second, you now have a velocity of negative 9.8 meters per second, right? It's negative because I'm going down. So you have to get used to, in motion problems, vertical, when you have negative motion, it just means you're traveling towards the surface. When you have positive motion, it means you're going away from the surface, and the acceleration is always acting down. All right. Now, when we use the equations of motion to calculate, we're going to find later that after 1 second, you are now negative 4.9 meters down below where you started. So you drop it after 1 second, you're 4.9 meters below the starting point. You're traveling with a velocity after 1 second of negative 9.8 meters per second, and the acceleration is the same as it always is. So now let's take a look at what happens after 1 more second. So after 1 more second, you're not going to be here. You're actually going to be farther down, right? Because you're accelerating. You're traveling faster and faster. So the ball is not going to be an equal distance down. It's going to be a little bit farther down. And so now we're going to explore what happens at the 2 second mark. Well, first of all, the acceleration due to gravity is still negative 9.8. This stays the same all the time. So at this point, what would the velocity be? This is 1 more second elapsed, and so then I have to subtract another 9.8 meters per second to my velocity, and so my new velocity is negative 19.6 meters per second. So I'm traveling a lot faster, right? What is my position? We use the equations of motion. We'll get to that later, but what you end up with when you do it is negative 19.6 meters below the surface. Notice after the first second, you only went about 5 meters, but 1 more second later, you dropped a whole lot more. Why? Because you're going a lot faster as you accelerate downward. All right, let's take a look at what happens at the 3 second mark. You're not going to be an equal distance here because you're accelerating. You're going to be even farther away down here. And so you're going to be somewhere way down here at the 3 second mark. 3 second mark. Okay? Now, what is the acceleration? The acceleration is the same as it always is. See how it's constant? See how constant acceleration works? It means it never changes, negative 9.8. What is the velocity going to be? Well, I was traveling at negative 19.6. If I subtract another 9.8 from that, I get 29.4, but it's negative 29.4 meters per second. You take the previous velocity after 1 more second and you subtract another 9.8 meters per second. You know, acceleration means meters per second per second. Everything's negative because you're going down, but it's the same concept as accelerating in a positive way. We just keep subtracting another 9.8 and going faster and faster in the negative direction. Now you're going really, really fast, 29 meters per second negatively. When we run it through the calculational engine over there with the equations, we figure out that we're 44.1 meters below the starting point. So after the first second, you only move about 5 meters. After the next second, you're down at almost 20 meters, and after the third second, you're almost at 45 meters. So you're covering so much more distance because your velocity is increasing so much. Now, I don't have room to really make the scale appropriate, but you can kind of use your imagination and say that, okay, if this is 1 second, 2 seconds, 3 seconds, 4 seconds is going to be basically off the board, but I can't put off the board, so I'm just going to put a dot here, and you're going to have to pretend that this is a wider gap here. After the 4th second, if I can use my colors correctly, after my 4th second, we have the exact same acceleration, negative 9.8 meters per second squared. And so what's our new velocity? This was our old velocity. We subtract another, or add another negative part to a negative 9.8 to it, and we have negative 39.2 meters per second. So we're going even faster. And then when we run it through the distance equations, what we get over here is negative 78.2 0.4 meters below the starting point. So it would have been very easy for me just to have written this on the board, open up the board, reveal it to you, but it wouldn't have the punch. I wanted to have the punch. I wanted to do it together so you can see how this works. When you drop an object, right, the acceleration due to gravity never changed. It's always the same. Now we know, because we did a little more work than typically we do even in a physics class, we did a little work to know that the acceleration really does depend on distance. But we assume it's constant, and any problem we use with gravity, we put 9.8, negative 9.8 in. So this column stays the same. Our initial velocity was 0. After the first second, we add this negative acceleration and get this. The next second, we add another negative 9.8. Then we add another negative 9.8. Then we add another negative 9.8. Because each second that goes by, we're subtracting or adding another 9.8 meters per second in the down direction to our velocity. And because we are traveling so much faster toward the end of the motion, we are covering so much more distance, then as each second ticks by, it's more and more and more and more distance. And this is why when you drop something, it doesn't start out very fast, but then as it accelerates, it starts covering a tremendous amount of distance very, very, very fast. So this is what constant acceleration means. It means that you're always gaining speed every second. And when you have more speed gain, you're covering distance even faster than you're really covering it in a quadratic way. This is like a squaring is really what's going on. We talked about that the position usually looks like a quadratic. It goes up very steeply like a parabola. You can see what's happening here. It's going up very, very steep. And if you graph this, it would look like this, like a parabola like that. All right, so in this lesson, we've done quite a bit. We said that for constant acceleration problems in the vertical direction, we just say the acceleration is equal to g, where g is the positive 9.8. And so since down is the negative direction, we say the acceleration is negative 9.8 in all of our problems. What we did over here as far as the equations go is we took all the equations of motion and we just put negative g everywhere we saw a, and we changed all the y's to x's, and we used the same equation in the vertical direction as from before. And then we did this in showing how the acceleration is constant. That leads to velocity increasing by the same amount every second, but the position is gaining way faster than that. That's quadratic in nature because of the nature of the derivatives and of the rate of change and so on. Because the velocity is always increasing, the position has to increase even faster than that. And then the most interesting thing we talked about in the whole lesson was why can we ignore mass when we're dropping things anyway? It's because, yes, it is true that a more massive object is pulled more with the force of gravity. If we have an object with a higher mass has a higher gravitational force, then yes, there is more force on this side of the equation, let's say by 1,000-fold. But at the same time, the only way we got the extra force of gravity was by increasing the mass by 1,000-fold. So this thing does go up and it does pull harder, but the mass also goes up. And these things go up together. Anytime you increase the force of gravity because of the other equation, you've also increased the mass. That's what we're talking about. And because you're increasing both of them on the same side, then and they're increasing by the same rate all the time because of the same root mass entry on both sides, the acceleration remains unchanged. Yes, the force of gravity gets bigger, but the mass gets bigger too, and those two things cancel out, which you can see more, I think, clearly here when the mass cancels out, and the acceleration due to gravity does not have any dependency on the mass of the object doing the falling. So I'm going to give you homework, and that homework is go to a video site, YouTube, whatever you use at the time that you're watching this video, and go look it up. Feather hammer drop on the moon. Just go type it. You'll find a grainy video, which they did in the 1960s or so, I think probably the 70s. But it's fascinating because a feather, like a little feather, and a hammer falls at exactly the same rate. And that is exactly because of the reasons why we have outlined in this lesson. So I could have short-circuited this whole thing. I could have just said, hey, acceleration of gravity happens. It's a constant acceleration. Put it in these equations and use it. And that would have been a 5-minute lesson. But I don't want to shortchange you on understanding one of the most interesting and amazing things in all of physics. Why do these things fall at the same rate? And people still study this. It's because the gravitational mass and the inertial mass, which governs kind of the resistance to motion, they're the same thing. But why are they the same thing? There's no law of physics that says that they have to be the same thing. Maybe it's because of a deeper connection. And in fact, Einstein made a lot of those deeper connections and created a new, much more robust theory of gravity, which we learn much, much, much later. which is a lot more complex than what we have here. And I don't want to get into that whole ball of wax right now, but it just suffice to say that the story is not over on gravity. Gravity is not just a force between two things as we have modeled it here. It's a great equation. We use it. It's pretty accurate, but the truth of what gravity is actually still being discussed and theorized about and studied even today. So don't think that all the problems are solved. There's still some big ones out there. So make sure you understand this and then follow me on to the next lesson. We're going to apply these equations of motion to free fall acceleration problems. Learn anything at mathandscience.com.